Hey guys, we are going to talk about chapter 14 today, which is the lymphatic system and immunity. So we'll start with the lymphatic system and some of the basics that you'll find in it. So the first component is going to be lymph. So this is composed of excessive interstitial fluid. Lymph is formed when plasma filters out of blood capillaries, enters the space between the tissue cells, and then the excess is going to enter the lymphatic capillaries as lymph. So the majority of that plasma fluid is going to go back into the capillaries, but anything extra is what gets picked up into the lymphatic capillaries. So once the lymph is out of the blood capillaries, it's going to go into the lymphatic vessels. And those are going to be made up of the lymphatic capillaries, lymphatic venules, lymphatic veins, and then the terminal vessels. So those are in order from smallest to biggest. So we'll start with capillaries, venules, veins, and then the terminal vessels, which are the right lymphatic duct or else the thoracic duct. These vessels are going to be composed of sheets consisting of a single cell layer of simple squamous epithelium. So this single cell layer makes it really easy for that fluid to go into those lymphatic vessels. The excess fluid goes right through that sheet of single cell layers. These vessels are also fitted with valves, and this is going to allow a one-way movement. So this helps assist in the movement of the lymph. So those terminal vessels that we mentioned are the right lymphatic duct, and this is going to drain all of the lymph from the right upper extremity, the right side of the head and neck, and the upper torso. All other areas are going to empty into the thoracic duct, which is our largest lymphatic vessel. It has an enlarged pouch called the cisterneculi. So this kind of serves as a holding area for that lymph. And this is going to get the lymph from the remaining 3/4 of the body. So if we're looking at a diagram here, you can see that this portion of the body is going into that right lymphatic duct, while all the rest of it is going to go into the thoracic. And then this picture just shows kind of how those capillaries, those lymphatic capillaries, sit on top of the blood capillaries. So you can see in this close-up, the plasma is going to filter out of the blood capillaries, and then most of it will go back into the blood capillaries, but the excess is going to go into the lymphatic capillaries, and then travel through those venules, veins, and then the terminal vessels. So the whole purpose of this lymphatic draining is to prevent the accumulation of too much tissue in the fluid. If we didn't have this process, then all that excess plasma that's getting pushed out of the blood capillaries would just hang out, and we'd end up with a lot of edema and swelling in our body. The other component of the lymphatic system is going to be the lymph nodes. So these play a role in lymph filtration, defense, and leukocyte formation. So the lymph is going to pass through the nodes as it travels from the point of origin, so the capillaries, to the terminal vessels. And these are located in clusters along the pathway of those lymphatic vessels. So once the lymph gets into the node, it's going to percolate slowly through the spaces, and those spaces are called sinuses. These are composed of lymphoid tissue, which is a mass of developing lymphocytes and other related cells. And they play a role in biological filtration. So the phagocytes that sit in the lymph nodes are going to alter the content of the filtered fluid. So this is biological filtration. And this prevents infections from spreading by acting on the bacteria and the abnormal cells. So the lymph is going to flow to the node through several afferent vessels. So several vessels are leading to the node, and then it's just going to leave through one efferent vessel. So that lymph gets kind of swished around in those sinuses, and then the phagocytes will destroy any bacteria or abnormal cells that they find. So this kind of shows lymph node function in a section of skin that's infected surrounding the hair follicle. So this would all be the infection here. So here would be our afferent lymph vessels. So they're going towards the lymph node, and then we just have that one efferent vessel there. And then this shows the lymphatic network that's associated with breast tissue. So you can see it's pretty extensive. There's quite the network of lymph vessels and lymph nodes found in the breast. And this is why breast cancer can metastasize so quickly, as it travels through the lymph throughout the rest of the body. Some of the organs that we'll see or masses of tissue that we'll see in the lymphatic system is the thymus and the tonsils. So the thymus is the small lymphoid tissue located in the mediastinum. So remember, that's going to be in the thoracic cavity. So located in the thoracic cavity, responsible for the production of T lymphocytes or T cells. So these are critical to the function of the immune system. We'll talk about them in just a little bit. The thymus is also going to secrete hormones called thymosin, which influence that T cell development. So the thymus is going to reach its maximum size at puberty, and by about age 60, half of it is going to be gone, and by age 80, virtually all of the thymus is gone. Three different types of tonsils that you'll see. We've got the palatine tonsils, which everybody kind of knows as the tonsils. If you open your mouth real wide, you can kind of see them on either side of the throat. Then the pharyngeal tonsils are also known as the adenoids, and the lingual tonsils are kind of behind the root of the tongue. So these tonsils are going to serve as our first line of defense. Anything that we're breathing in is getting captured by the tonsils. So they are subject to chronic infection and enlargement. Enlargement of particularly the pharyngeal tonsils can impair breathing. So this just kind of depicts the different areas that you'll see the tonsils. So here's our palatine on either side, pharyngeal. It looks like it's directly on the roof of the mouth, but it's actually kind of back behind the palate. And then the lingual tonsils are going to be behind the root of the tongue, so back by that hyoid bone. Last but not least, we have the spleen, which is going to be the largest lymphoid organ in the body, located in the left upper quadrant, lateral to the stomach. So unfortunately, this is most often injured by trauma to the abdomen. And the functions are going to include phagocytosis of bacteria and those old red blood cells after they've filtered around the body or floated around the body and completed their lifespan. They will head to the spleen. It also acts as a blood reservoir. So the spleen can contain more than 500 milliliters of blood. So if there's trauma to it, that's where you get the potential for that excessive bleeding inside the abdomen. Some functions of the immune system, mostly it's going to be protection. So it's protecting the body from pathological bacteria, foreign tissue, and cancerous cells. So because its main role is protection, it's made up primarily of defensive cells and molecules. A couple different types of immunity that we'll find in this system. The first one is nonspecific, also referred to as innate immunity. This one does not require prior exposure to an antigen. So it's kind of an overall generalized protection. The skin and the mucous membranes are considered nonspecific barriers, so they prevent entry into the body from any invading substances. Some examples of nonspecific immunity or response that the body has are tears. So if we get a harmful substance from the eye, it doesn't really matter what that substance is. We'll have a generalized reaction of that tear production. The other one is mucus, which traps the foreign material that we're inhaling or breathing in. So again, doesn't matter what we're inhaling. It could be cold virus, it could just be sawdust. Regardless of what it is, we'll produce that mucus to capture it. One response that's pretty common with this nonspecific immunity is the inflammatory response. And this is going to attract immune cells to the site of the injury, characterized by increased blood flow, vascular permeability, which promotes the movement of white blood cells. So some common symptoms that you'll see with this are heat, redness, pain, and swelling. This is also a sign that there is an infection. So that inflammatory response can occur. If you've cut your hand on something, it might not look bad to start, but the next couple days it gets that heat and swelling and it's painful. That's an inflammatory response. So this is in your book as well, but this table breaks down the different mechanisms of nonspecific defense. So you can see different secretions here. So sebum, mucus, inflammation, fever is kind of a nonspecific defense. And then this just shows the cycle of the inflammatory response. So we have healthy tissue to start, then bacteria is going to enter in. This results in tissue damage, and then inflammation mediators are released. So then three things will happen. We'll have chemotaxis, which is the movement of cells, increased blood flow, and then increased vascular permeability. So this is what's causing those white blood cells to be able to reach the tissue damage. So again, increased number of leukocytes, those white blood cells. The bacteria is contained, destroyed, and phagocyzed. And then if there's no bacteria remaining, the tissue becomes repaired and we go back to having healthy tissue. If the bacteria does remain, then additional mediators are activated and we start this process all over again until we can get to no bacteria remaining. So we talked about non-specific immunity. Now we'll touch base on specific immunity, which is also referred to as adaptive immunity. This is because the body has the ability to recognize, respond to, and remember harmful substances. So the body has adapted to have the ability to specifically fight these particular bacteria. So it's broken up into two different types, natural and artificial, and then those are each broken up into active or passive. So natural immunity is when exposure to the causative agent is not deliberate. So anything basically aside from a vaccine is going to be a natural immunity. So if you've gotten the chickenpox from a kid at daycare, that's a natural exposure to it. So then the processes of active versus passive in this scenario, this would be an active exposure. You are actively exposed to the disease that produces immunity. Passive is going to be when the immunity is passed from the mother to the fetus, either through the placenta or the mother's breast milk. So natural active would be primary exposure to the causative agent, not deliberate. Natural passive would be either through the placenta or the breast milk from a mother to a fetus. Artificial immunity means that the exposure to a causative agent is deliberate. So this is vaccines, anything along those lines. So active means that a vaccination results in activation of the immune system. So during active artificial immunity, they are giving, say, the flu virus. They give you kind of a dead version of it so that your body will have an immune response and form those antibodies needed to remember it. Passive artificial occurs when the protective material or the antibodies are developed in another individual and then given to a non-immune individual. So instead of injecting a dead version of or an antigen, we are injecting the actual antibodies. These processes are probably the most confusing portion of this chapter. So if you have any questions about this or want to visit more, just shoot me an email and we can talk. These are found in your book, just detailing the different types of immunities and then examples of those. So some molecules that we will find in the immune system are cytokines, which are chemicals released from cells that act as direct agents of innate, non-specific immunity. And then the other one is going to be antibodies, which are protein compounds with specific combining sites. So this is going to play a role in our humoral immunity or antibody-mediated immunity. What happens with the antibody, so it's specific to a particular antigen, and remember that an antigen is bacteria, invading cell, anything that the body doesn't recognize as being its own. So a particular antigen is going to trigger that specific antibody. So when that happens, we have an antigen-antibody complex. Which results in a couple of things. It can either neutralize the toxin, clump or agglutinate the enemy cells, or promote phagocytosis. So here kind of shows us our different pathways that this antigen-antibody complex can result in. So the first one, if we're looking at this antibody, so remember it's particular to this antigen. If any other antigen comes into the body, it's not going to trigger this specific antibody. It might trigger a different antibody, but not this one. So these two have to be compatible. First thing it can do is going to just inactivate the antigen. So it kind of grabs it and holds on and doesn't let it do anything else. Another option is to bind those antigens together. So this is agglutination or clumping. So you can see it is essentially inactivating it by closing off the antigen between two antibodies. We could have phagocytosis occur, so that phagocytic cell is going to come in and eat that antibody antigen. It could attach to the antigen could attach to the antibody, which is then going to attach to a different cell and initiate the release of inflammatory chemicals, or else it could activate the complement cascade. So the complement cascade we will talk about in just a second, but it's going to result in bacteria, the actual bacterial cell bursting, which is then going to result in inflammation, the attraction of white blood cells, and cell destruction. So those complement proteins are going to trigger a rapid fire cascade called the complement cascade. So the complement proteins are going to form a donut-shaped hole in the bacteria's plasma membrane. Water is going to enter into the cell through that hole, and it's going to cause the bacteria to burst. So if we're looking at it in a picture, these are the complement, okay? And they're going to kind of form together on here, bore a hole into the bacterial cell, and then we're going to have this influx of water that's going to go into the cell, and eventually it just bursts. The complement proteins are also responsible for attracting immune cells to a site of infection, activating those immune cells, marking a foreign cell for destruction or increasing permeability of blood vessels. Another type of cell that we'll see are phagocytes. So these are responsible for ingesting and destroying foreign cells or other harmful substances. So different types are going to be neutrophils, monocytes and macrophages, and dendritic cells. So neutrophils are short-lived phagocytic cells. They commonly act on pus, like you would find in a pimple. Monocytes turn into macrophages once they are inside of the tissue. The macrophages are just going to kind of run around the tissue and eat bacteria when they find them. So if they happen upon a bacteria, they'll just kind of chomp it up. And then dendritic cells are found in the mucous membranes near the external surfaces. So they provide protection from those threatening particles as soon as they're entering into the body. One thing to note is that macrophages and dendritic cells are going to act as antigen-presenting cells. So once they ingest an antigen, they will display the calling card of that antigen on their outer surface so that they can trigger those specific immune cells or the antibodies. So here we have bacteria on the outside. This would be the phagocytic cell, so the macrophage. Those bacteria are going to attach to non-specific receptors. The phagocytosis is going to begin, so the cytoskeleton extends that plasma membrane to wrap around the bacteria. The lysosome is then going to act on the bacterial cell, and eventually those end products of the bacteria after they're destroyed will be released, and then the cycle just repeats. So I think of it as kind of eating the bacteria, it's going to digest it, and then it basically burps out the extra stuff. So the last ones that we'll talk about are the lymphocytes. So these are the most numerous of the immune system cells, broken up into two major types, which are B cells and T cells. So we'll go through the development of the B cells first. So during the first stage, the stem cells are going to develop into immature B cells. So this takes place in the liver and bone marrow before birth, and then once we're into the adult stage, it is only in the bone marrow. After these B cells mature, they are inactive, but they're going to migrate to the lymph nodes. So the second stage is going to result in the activation of the B cell. So once that inactive B cell comes in contact to the antigen, it's going to bind to the surface antibodies on the B cell. So this is going to start the process of activation, which results in the B cell dividing repeatedly, forming two clones of the B cell. So we have the plasma cell and the memory cell. So the plasma cell is going to secrete antibodies into the blood. And then the memory cells are actually going to be stored in the lymph nodes. So they just kind of hang out in the lymph nodes until that particular antigen is seen again. And then they are already activated. so they can act on that antigen right away. If the subsequent exposure to the antigen occurs, the memory cell will then kind of turn into the plasma cell to secrete the antibodies. So these play a role in humoral immunity, which is the resistance to invading organisms by antibodies. So this diagram just kind of shows the process of that development. So it starts as a stem cell. It's going to develop into immature B cells. So you can see the antibodies sticking out of the B cell. The mature B cells, so they're still inactivated at this point, but they're going to travel to the lymph nodes. Once they're in the lymph nodes, if they are activated by a particular antigen, so you can see here now that antigen is sitting on top of that antibody, they're going to divide rapidly and repeatedly to form clones of themselves. So we'll get two types of cells from this, memory cells and then the plasma cells. So the plasma cells are going to secrete antibodies into the blood, which is then going to circulate and look for these antigens. The memory cells are going to be stored in the lymph nodes, waiting for subsequent exposure to that antigen. If that occurs, then they become plasma cells and secrete the antibodies into the blood. And if we go back to this slide, so this would be the antibody that's been released, then it can start one of these processes depending upon which one is best for that particular antigen. So we have the development of T cells. So the stem cells from the bone marrow are going to migrate to the thymus gland. During the first stage, those stem cells will develop into T cells. After that, they're going to migrate to the lymph nodes, where they're going to develop into activated T cells. So this occurs, same as those B cells, if the antigen binds to the T cell, then it's going to activate it. So this plays a role again in humoral immunity, so resistance of a disease due to antibodies. So here we can see kind of that process, very similar to those B cells, but the stem cells are going to develop into the thymus. They're going to go to the thymus, develop into inactivated B cells, where they then go to the lymph nodes. Might find some in the liver and the spleen as well, but primarily lymph nodes. There, if an antigen binds to the T cells, it's going to activate it. And that's going to result in memory cells or effector cells. So the effector cells are going to go on to kill the infected cells, tumor cells, whatever the process is that's causing this response. Memory cells, again, are just going to kind of hang out and wait for the antigen to come back if it ever does. So some T cells can move on to produce cell-mediated immunity. So this is going to be resistance to a disease or the organism that causes a disease resulting from the actions of cells. So there's 3 different types of cells that can play a role in this. Cytotoxic T cells will kill infected or tumor cells by releasing a substance that poisons them. Helper T cells will release chemicals that attract and activate macrophages to kill those cells by phagocytosis. And then regulatory T cells release chemicals to suppress the immune responses. So here we can see if we have one of those activated T cells, and it's performing a cell-mediated immunity, we can have cytotoxic, helper T cells, or regulatory T cells. And then this just provides details of what those specific T cells do. And that is chapter 14. The biggest, I think, area on this that gets to be a little bit confusing are those different types of immunity, and then B cells versus T cells and the processes associated with those. So if you have any questions at all, please contact me and we can talk it through.